Now, what's the probability of the observed result in terms of p? So, if we got 3 h's, that sets the random variable to 3, right? Okay, so the probability that the random variable x took the value 3, given some value for small p, probability that x is equal to 3 is 10 choose 3, p to the 3, 1 minus p to the 7. Okay. Now, we're going to consider this value, f sub x, 3p. We're going to think of that as a function of p. Okay? And we call this function the maximum likelihood function. And we typically write it as capital L of p semicolon 3. Okay? So we had the experiment. We got 3 of these. And for different values of p, you could still get 3. But we're going to try and find the value of p which made a result of 3 the most likely out of all the possible results. Okay? All right. So here's a graph of this function. Okay. So here's a graph of this function. Right. Remember, this was the function. The PMF when x is equal to 3, for x equals 3, was this. So we take different values of, so this is your L, right, in the vertical axis. And these are the values of p. P is a probability. It can go from 0 to 1. So the result of 3 is most likely at, well, what we intuitively said. You have a maximum, right? So this maximum likelihood function has its maximum at p is equal to 0.3. Okay? Okay. Typically, we don't work with the maximum likelihood function. Okay.
You did 10 tosses and you got 3 notes.
Yeah, I did 10 tosses. I got 3, right? So the probability of getting that result is this number from the PMF. Right? The PMF says that f sub x of 3 is 10 choose 3, p to the 3, 1 minus p to the 7. Right? So then p could in principle be anything. But we say, this is what we actually got. So what is the value of p for which the result x equals 3 is the most likely? Well, we intuitively said that that was 0.3. And now, if we take this function, this is a function of p, right? So we plot the value of the maximum likelihood function versus p. Well, it turns out that it's 0.3. In fact, that is the most likely. Okay? All right? So, now, as I said, typically, instead of working with the maximum likelihood function, we work with the logarithm of that function. Okay? Log's an increasing function, so finding the maximum of the maximum likelihood function is the same as finding the maximum of the p which maximizes the log likelihood function. Okay? And typically we write that with a small l. Okay? Yeah.
Why do we take the log for it?
Quite often it makes our calculations easier to take the logarithm than the original function.
So it's now log.
Well, so we would say, what maximizes this function? What p maximizes this function? Well, p equals 0.3. So if we take the logarithm of this function, p equals 0.3 will also maximize the log likelihood, right? No. P maximizes this function, which is this. A p of 0.3 maximizes this function, okay? A p of 0.3 will also maximize the logarithm of this function, okay? So you're going to get the same p, right? Except because you're working with logarithms, you know, sometimes you have exponentials, sometimes you have factorials, the numbers can get rather large. So the logarithm helps to tame that, right? Okay. Okay. So now I had that original function. Capital L was f sub x of 3p. Okay? Now if I take the logarithm of that, I get this function instead. It's still a function of p going from 0 to 1. And the maximum value of this function is still occurring at p is equal to 0.3. Okay, so that's one example of this idea of maximum likelihood estimation of a parameter. Okay. No, we're going to find the where the maximum occurs using taking derivatives and setting them equal to 0. Right. Okay. Okay, so the maximums are occurring for the same value of p for both of these. The likelihood function, the max likelihood function, and also the log of the max likelihood function, the maximums are occurring at the same p. And it's this value of p that we're interested in. Okay. So, how do we do optimization? Well, typically we take derivatives and we set them equal to 0. At what value does the derivative equal 0, right? Okay, so let's do it for this function. We take the derivative with respect to p of the log likelihood function. Okay, well, that was the derivative with respect to p of the logarithm of the PMF when x is equal to 3. So 10 choose 3, p cubed, 1 minus p to the 7. Okay? So that's the derivative with respect to p, and now we use the property of logarithms, right? Log of ab, a times b is logarithm of a plus the logarithm of b. So we do that for all these terms. That's logarithm of 10 choose 3 plus 3 log p, right? So logarithm of p to the n is, right, n log p, right? So 3 log p plus 7 log of 1 minus p. Okay, now notice that this part here, so here's the benefit of taking the logarithm. This part here is a constant, right? So that just drops out. See, all these terms become very simple because we're taking the logarithm, right? So derivative of 3 log p with respect to p is 3 over p, and derivative of 7 log p is 7 over 1 minus p times minus 1. So there you go. Okay. So that is going to be equal to 0 at a maximum. The derivative is going to be 0 at a maximum. Okay, so then we do a little bit of algebra. We will get that this will be equal to 0 when p is equal to 3 over 10. Okay, so p equals 3 over 10 maximizes the log likelihood function. Therefore, it maximizes the likelihood function. And that's one way of estimating what p is. We can't know what it is exactly. Right? P could have been 0.01, and you could still get x equals 3. It's just that would be that result would be less likely than this result. Right? You're most likely to get a result of x equals 3 when p is equal to 3 over 10. Okay? Okay, so this is our estimate. Remember, it's an estimate. P equals 0.3. Okay. That okay for that example? All right, next example. All right, so we're conducting an experiment. Each experiment can result in 3. So the result will have 10. The experiment will consist of 10 independent trials. Each trial can result in 3 outcomes. Let's call the outcomes A, B, and C. And we believe that they occur, A, B, and C occur with constant probabilities, P sub A, P sub B, and P sub C. Right? So now we've got 3 parameters in this problem. What kind of random variable do we use for this? The multinomial random variable, yes? Okay. So let's say we do the experiment, and let's say result A occurs n sub A times, the result B occurs n sub B times, and the result C occurs n sub C times. Okay? And we must have that n sub A plus n sub B plus n sub C is equal to the total 10 trials. Okay, so let's say we did that, and we found that n sub A is equal to 7, n sub B is equal to 2, and n sub C is equal to 1. So now, intuitively, before we do any math, how would you estimate the probability of A, result A, probability of result B, probability of result C? Yeah, so I would estimate P sub A equals 0.7. I would estimate P sub B is equal to 0.2, and P sub C is equal to 0.1. Okay, let's see if we can justify that. Okay. All right, so my multinomial random variable says that the probability in 10 trials of getting A n sub A times, result B n sub B times, and result C n sub C times, right? That's 10 factorial over n sub A factorial, n sub B factorial, n sub C factorial. The probability of A to the power n sub A, the probability of B to the power n sub B, and the probability of C to the power n sub C. That's your multinomial coefficient. Okay, I can think of n as a vector if I want, with elements, with entries n sub A, n sub B, and n sub C. Yes, This multinomial coefficient is defined to be 10 factorial n sub a divided by n sub a factorial n sub b factorial n sub c factorial. Okay. Okay, so I can think of these as vector quantities. So the vector n has these three entries. The vector p has entries p sub a, p sub b, p sub c. And I have to have that n sub a, n sub b plus n sub a plus n sub b plus n sub c is equal to 10. And I have to have that the probabilities p sub a, p sub b, and p sub c, they must sum to 1. Okay. Now, in our particular case, the maximum likelihood function, we had results for a, b, and c. We had a 7 times, b 2 times, c once. So if we put these in for n sub a, n sub b, and n sub c, then this is the function. So this is a function of these three probabilities, right? And they have a constraint on them that these individual probabilities have to sum to 1. Okay? And we want to find the maximum of this function. Okay. So we take the logarithm of that function. That's the log likelihood function. So that's the log of the multinomial coefficient plus 7 times the log of p sub a plus twice the log of p sub b plus 1 times the logarithm of p sub c. So I take the logarithm of that. And we keep in mind the constraint that the probabilities p sub a, p sub b, and p sub c, they must sum to 1. Okay. And note that when we now, so who's done calculus 2? Okay. So if you've done calculus 2, you've seen the method of Lagrange multipliers. If not, you're right, right. So the idea is that, okay, so we had this. So you've got, you're going to take the partial with respect to p sub a. So when you take the partial with respect to p sub a, first term goes to 0. Next one will be 7 over p sub a. That's the partial derivative of L with respect to p sub a. Okay? Now you take the partial derivative with respect to p sub b. So the partial derivative of L with respect to p sub b is equal to 2 over p sub b. Okay? Then you take the partial derivative with respect to p sub c. So the partial of L with respect to p sub c is equal to 1 over p sub c. Okay. Now you also had a constraint. Right? The method of Lagrange multipliers helps you deal with optimization problems when you have a constraint. The constraint was that p sub a plus p sub b plus p sub c is equal to 1, or that the sum of the probabilities minus 1 is equal to 0. Okay? So the method of Lagrange multiplier says that the derivative of the function you're trying to optimize with respect to p sub a is going to be equal to some constant that you don't know, typically we call it lambda, times the derivative of this constraint with respect to p sub a. So that derivative of p sub a of this is 1, right? So, yeah.
If you would write the demand function, would it just be all of that minus lambda brackets the constraint? Would that be the demand function?
Yeah. Okay. So this is, okay, so the derivative of the function we're trying to optimize with respect to p sub b is equal to lambda times the derivative of the constraint with respect to p sub b. And the derivative of what we're trying to optimize with respect to p sub b, take the derivative with respect to p sub c, and that's equal to the derivative of lambda times the derivative of the constraint with respect to p sub c. Okay? So that's how you set up your problem using Lagrange multipliers. Okay. And you keep your constraint in mind that, well, either this way or you write that the sum of this is equal to 1. Okay. Okay. Now, if I can rearrange this a little. So I've got a system of 4 equations. I've got the equations that come from the derivative plus the constraint equation. So I've got 4 equations that I need to solve. Okay? And I can rewrite them a little bit. Right? I can rewrite this as 7 over, I can move the lambda downstairs, divide by lambda, and multiply by p sub a on both sides, and I will get 7 over lambda equals p sub a. I can divide by lambda on both sides of this and multiply by p sub b on both sides of this equation, and I get 2 over lambda equals p sub b. Okay? And then I can multiply by p sub c on both sides of this equation and divide by lambda on both sides of this equation. I get 1 over lambda equals p sub c. Then I can take these results and put them into the constraint equation. So p sub a I replace by 7 over lambda. P sub b over here I replace by 2 over lambda. P sub c over here I replace by 1 over lambda. And that's supposed to be equal to 1. So what do I get for lambda? I get lambda is equal to 10. Okay? So all of this put together, right? So all of this plus that, all of that gives me lambda is equal to 10. Now, once I have lambda is equal to 10, I put it back in here. P sub a is equal to 7 over 10. P sub b equals 2 over 10. P sub c equals 1 over 10. Okay, so. Okay, and this is what we said intuitively. We believe that it would be. Okay. Okay. Let's make it a bit more interesting. Okay, so I have Poisson random variables. They are identical, so they all have the same parameter lambda. Okay? And so, and they're independent. Okay? So the probability of xi, the probability that the ith random variable takes the value xi is 1 over, sorry, that should be not x1, xi factorial times the exponential e to the negative lambda, lambda to the xi. Okay? We don't know lambda, we want to estimate it. Okay. So, let's say we observe that x1 takes the value small x1, x2 takes the value small x2, xn takes the value small xn. So we're watching all of these. We do our experiment, we determine, and we get some values for these random variables, okay, at the end of the experiment. What's the probability of getting these values? Well, they're independent, so the probability of getting that set of values is the product of the individual probabilities, right? So it's the product from I equals 1 to n, the probability that xi equals small xi, which is this here. Okay, so it's the probability of all these Poisson probabilities given by the Poisson PMF. Okay, so this is, now if we think of this as a function of lambda, that's our maximum likelihood function. And the logarithm of that would be the log likelihood function. Okay, now note that this exponential lambda, negative lambda, is a constant, so it can be pulled out of the product, right? And then this is a product of 1 over the xi's, right? So that can be thought of as 1 over the product of the xi factorials. Okay, and then we keep, that's lambda to the x1 times lambda to the x2 times lambda to the x3, so rules of exponents. That term gives us this lambda to the x1 plus x2 up to xn. Is that okay? All right. Well, okay, so this is our maximum likelihood function. And we're thinking of it as a function of lambda. Now, if we take the logarithm of that, right, the log and exponential cancel each other out, so negative lambda n plus the sum of the xi's logarithm of lambda, and then we're subtracting the logarithm of this product. Okay? So there's a lambda here, there's a lambda here, there's no lambda in here. Okay? Now, we take the derivative and set it equal to 0. So once again, this term, when you take its derivative, is going to go to 0. So this is minus, so the logarithm of this would be, we've already taken the logarithm. So when we take the derivative, this with respect to lambda, this will be a minus n. This is a constant as far as logarithm is concerned. Then you get a 1 over lambda. And this has no lambda in it, so the derivative is going to be, of that part is going to be 0. Okay, so this is what we get. Okay, and then our estimate for lambda, which makes that equal to 0, is the, well, it's the mean of the xi's that we got. Okay, what's the expectation?
X minus X bar.
Yeah, okay, so, all right. So we estimate our lambda as the average of the results that we saw when we did our experiment. Okay, so for example, if we had n is equal to 10, and we got x1 is 0, x2 is 1, x3 is 0, and so on. Then we would take the average of that, and we would say my estimate for lambda is 0.7. Right? Okay. Now, so we did a bunch of examples. Let's just get a formula for the general case now. Okay, so the outcome of the experiment might be several different things, right? So we can represent that as a vector. We have a random vector x, and it has a PMF or a PDF f sub x. And the various values that x can take are written as a vector small x. Okay? So this PMF or PDF might have a bunch of parameters, and we think of them as entries of a vector, and typically it's called theta. Okay? And that's unknown. Okay? And so we take our PMF or our PDF, and this x is some result after the experiment. The values of the x, the various values are set. The outcomes are given. And this probability of getting that result is thought of as a function of theta, the vector of parameters that we don't know. Okay, and so this probability that's called the maximum likelihood function. All right, and we will take the logarithm of that, usually written small l, and the principle of maximum likelihood is we look for the theta that maximizes the log likelihood function. And so that's, again, this is a way of hopefully relating the theory that we've done to some real life analysis.